In this lesson, we'll begin our unit on chemical equilibrium, one of the most important topics in chemistry. Equilibrium doesn't mean that the reaction stops. It means that the forward and the reverse reactions balance each other. Rather, like this mole is constantly shifting his weight back and forth to maintain his balance. He's not just sitting still. We'll walk through what reversible reactions are, what equilibrium looks like at the particle level, and how we express equilibrium mathematically. By the end, you'll be able to explain what it means for a reaction to be in balance and how to write an equilibrium constant expression. So up until this point, we have been discussing irreversible reactions. This is where the reactants combine to form the products and the reaction stops once the limiting reagent has been completely used up. Only the forward reaction occurs. So in the example, we have the single replacement reaction between gold 3 oxide and iron to form gold metal and iron 3 oxide. Now, if you remember the activity series, gold is at the bottom of the activity series, so that means that, and iron is above it. So that means that while iron is capable of replacing gold in a compound, gold cannot replace iron in a compound. Its activity is too low. So this is an example of a reaction that only goes in one direction. Reversible reactions are where you have both the forward and the reverse reaction occurring to a significant degree. So for example, we have one of my favorite reactions, the synthesis of ammonia. It's called the Haber process. And the thing is that in order to get that triple bond in nitrogen to break, this reaction has to take place at a fairly high temperature. But unfortunately, the high temperature will cause the bonds in the NH3 to break, causing it to go back to form the hydrogen and the nitrogen reactants. However, even though we have the reverse reaction, hydrogen and nitrogen are still the reactants, and ammonia is still the product for this reaction. So instead of writing out this reaction twice, instead we're going to use a double-headed arrow. And there are multiple ways of doing a double-headed arrow. It just depends on which font is chosen. So don't let it throw you off if you see it look like this, and sometimes it looks like a single stick with two arrows on it. The point is that it's pointing in both directions. So a reaction is at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. So looking back at this example, we have just as much ammonia being formed as we have ammonia being broken back down to reform the reactants. The general form of the equilibrium constant, which is capital K, lowercase k means something else, is going to be the molar concentration of the products divided by the molar concentration of the reactants. If you have coefficients on your reactants or products, they're going to show up as the powers on these concentrations. One of the big mistakes that people make when they first start working with equilibrium constants is they just put the entire expression, so we'd have that plus in there, over your products over reactants. When you're talking about equilibrium, it's just multiplication and division. There is no addition or subtraction. Since K is just a ratio of the amount of products that you have versus the amount of reactants that you have at equilibrium, that means that if you have a K that is bigger than 1, then you have more products than reactants present at equilibrium. And this reaction is product favored. This is the kind of reaction that chemists want. On the other hand, if you have more reactants than products at equilibrium, your K value is going to be less than 1, and this will be called reactant favored. There are some reactions that are like this, and there are a number of different tricks where we can get it to make more reactant, more product than would normally be expected for a reaction at equilibrium. So here is a graph of concentration versus time for the synthesis reaction that I mentioned earlier. We're going to start our concentrations. So we start off with a high concentration of hydrogen, moderate concentration of nitrogen, and no NH3 at all. and then at a certain point in time, all of the concentrations level off and they stop changing. It does not mean that the reaction has stopped. It just means that we have established an equilibrium. So we can set up our equilibrium constant expression, products over reactants, and then raise those different molar concentrations by the coefficient in the reaction equation. So heterogeneous equilibria occurs when you have reactants and products in more than one state. So the one that we saw in the previous slide, everything was in the gaseous state. On the one on this slide, we have barium, and we also have the ions dissolved in water. So one of the reasons why we like heterogeneous equilibria is that we can get rid of the values for some of the different things that are in this equilibrium. And that is because the molar concentration of solids and liquids doesn't change as a result of being in this equilibrium. And we're going to say that they have the effective concentration value of 1. So that means that the equilibrium constant for barium solid being in equilibrium with its ions is going to be just the molar concentration of the barium ions times the molar concentration of the chloride ions squared. Because this refers to a very specific situation where you have a solid in equilibrium with its ions in solution, it gets a special designation shown as a subscript. Capital K always means equilibrium constant, products over reactants. And then we use different subscripts to say if it's a special case. Like in this case, it's solid dissolved in, or solid in equilibrium with its ions. It'd be the solubility product constant. So rather than writing KEQ, which is just a little redundant, instead we would replace that with KSP. And that would tell whoever's looking at it what the original reactant was. So here we have some more examples. And then I just have the equilibrium, the generic equilibrium constant expression up here at upper right. And have an example. The water has an equilibrium value of, liquid water has an equilibrium value of 1. And I'm going to switch over to my pen. So in this case, this one has a value of 1, and this is the only one that's going to show up in the equilibrium expression. So it's just going to be equal to equilibrium constant. It's going to be equal to the gaseous concentration of the water. So down here, we have a solid, so we know that one's going to be a 1. So our equilibrium constant is going to be 1 over the C10H8 in the gaseous phase. For the next one, again, we got a solid, so that's going to have a value of 1. The calcium oxide also has a value of 1. So that means our equilibrium constant is going to be just equal to the molar concentration of the carbon dioxide. We look at example 3. Here we have our carbon is 1. Water is a gas in this case, so it's still going to show up. Everything else is a gas, so it's going to be CO2 times 2H2 divided by H2O squared. And then our last one, we have iron 2 oxide, so that's going to be a 1 because it's a solid. And then CO, carbon monoxide, is a gas, so that's going to show up. The iron is a solid on the product side, so that has a value of 1. So we just end up with an equilibrium constant of the molar concentration of CO2 divided by the molar concentration of carbon monoxide. Another thing that we can do is we can use the equilibrium constant that has already been solved for a particular equilibrium, use it to figure out what an unknown concentration is. So A lot of times when you have these wordy problems, it helps to go through and identify what things are. So it says the equilibrium constant for the reaction below at 700 K. This is not the equilibrium constant. That's the temperature. And we are not looking at how temperature affects equilibria. That would be more for an advanced chemistry class. So this 0.44 is what our K actually is. And then it gives us the numbers for the water concentration and carbon monoxide and for the H2 concentration. So we go ahead and we set up our equilibrium expression, products over reactants, fill in the values, and then now we're going to solve for the concentration of the carbon dioxide. And punch the buttons on the calculator for a little while, and you get that the molar concentration of the carbon dioxide is 0.075 molar. All right, so we've hit the end of this particular lesson. So we've looked at the difference between irreversible, it only goes one direction, versus reversible. We also looked at dynamic equilibrium. The reason why it's called a dynamic equilibrium is because the reaction is still taking place. It's just that dynamic equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. We saw that for the equilibrium constant, it's going to be the ratio of the products to the reactants. So products up in the numerator, reactant molar concentrations down in the denominator. And that you have to remember that coefficients are going to show up on our equilibrium constant as powers. If you have a equilibrium constant that is bigger than 1, that means this reaction does what we want it to, it's product favored. If you have an equilibrium constant that's less than 1, that means it's reactant favored. And we saw that heterogeneous equilibria is when you have the reactants and products in different states of matter. And the reason why we like this is because we can assign a value of 1 to solids and liquids, and we don't have to do any math with them. All right, so that's it. Thanks for listening.